This figure shows a swimming pool that is full of water and surrounded by a concrete patio. Figure 3.1. The water in a swimming pool is a complex mixture of substances whose relative amounts must be carefully maintained to ensure the health and comfort of people using the pool. Credit, Modification of Work by Vic Brinkat. Chapter Outline. 3.1 Formula Mass and the Mole Concept. 3.2 Determining Empirical and Molecular Formulas. 3.3 Molarity. 3.4 Other Units for Solution Concentrations. Swimming pools have long been a popular means of recreation, exercise, and physical therapy. Since it is impractical to refill large pools with fresh water on a frequent basis, pool water is regularly treated with chemicals to prevent the growth of harmful bacteria and algae. Proper pool maintenance requires regular additions of various chemical compounds in carefully measured amounts. For example, the relative amount of calcium ion, Ca2+, in the water should be maintained within certain limits to prevent eye irritation and avoid damage to the pool bed and plumbing. To maintain proper calcium levels, calcium cations are added to the water in the form of an ionic compound that also contains anions. Thus, it is necessary to know both the relative amount of Ca2+ in the compound and the volume of water in the pool in order to achieve the proper calcium level. Quantitative aspects of the composition of substances, such as the calcium-containing compound, and mixtures, such as the pool water, are the subject of this chapter. Learning objectives. By the end of this section, you will be able to calculate formula masses for covalent and ionic compounds, define the amount unit mole and the related quantity Avogadro's number, explain the relation between mass, moles, and numbers of atoms or molecules, and perform calculations deriving these quantities from one another. Many argue that modern chemical science began when scientists started exploring the quantitative as well as the qualitative aspects of chemistry. For example, Dalton's atomic theory was an attempt to explain the results of measurements that allowed him to calculate the relative masses of elements combined in various compounds. Understanding the relationship between the masses of atoms and the chemical formulas of compounds allows us to quantitatively describe the composition of substances. Formula mass. An earlier chapter of this text described the development of the atomic mass unit, the concept of average atomic masses, and the use of chemical formulas to represent the elemental makeup of substances. These ideas can be extended to calculate the formula mass of a substance by summing the average atomic masses of all the atoms represented in the substance's formula. Formula mass for covalent substances. For covalent substances, the formula represents the numbers and types of atoms composing a single molecule of the substance. Therefore, the formula mass may be correctly referred to as a molecular mass. Consider chloroform, CHCl3, a covalent compound once used as a surgical anesthetic and now primarily used in the production of tetrafluoroethylene, the building block for the anti-stick polymer Teflon. The molecular formula of chloroform indicates that a single molecule contains one carbon atom, one hydrogen atom, and 3 chlorine atoms. The average molecular mass of a chloroform molecule is therefore equal to the sum of the average atomic masses of these atoms. Figure 3.2 outlines the calculations used to derive the molecular mass of chloroform, which is 119.37 atomic mass units. A table and diagram are shown. The table is made up of 6 columns and 5 rows. The header row reads element, quantity, a blank space, average atomic mass, AMU, a blank space, and subtotal, AMU. The first column contains the symbols C, H, Cl, and a blank merged cell that runs the width of the first 5 columns. The second column contains the numbers 1, 1, and 3, as well as the merged cell. The third column contains the multiplication symbol in each cell except for the last merged cell. The fourth column contains the numbers 12.01, 1.008, and 35.45, as well as the merged cell. The fifth column contains the symbol equals in each cell except for the last merged cell. The sixth column contains the values 12.01, 1.008, 106.35, and 119.37. There is a thick black line below the number 106.35. The merged cell under the first 5 columns reads molecular mass. To the left of the table is a diagram of a molecule. 3 green spheres are attached to a slightly smaller black sphere, which is also attached to a smaller white sphere. The green spheres lie beneath and to the sides of the black sphere, while the white sphere is located straight up from the black sphere. Figure 3.2. The average mass of a chloroform molecule, CHCl3, is 119.37 atomic mass units, which is the sum of the average atomic masses of each of its constituent atoms. The model shows the molecular structure of chloroform. Likewise, the molecular mass of an aspirin molecule, C9H8O4, is the sum of the atomic masses of 9 carbon atoms, 8 hydrogen atoms, and 4 oxygen atoms, which amounts to 180.15 atomic mass units, figure 3.3. A table and diagram are shown. The table is made up of 6 columns and 5 rows. The header row reads, element, quantity, a blank space, average atomic mass, AMU, a blank space, and subtotal, AMU. The first column contains the symbols C, H, O, and a merged cell. The merged cell runs the length of the first 5 columns. The second column contains the numbers 9, 8, and 4, as well as the merged cell. The third column contains the multiplication symbol in each cell, except for the last, merged cell. The fourth column contains the numbers 12.01, 1.008, and 16.00, as well as the merged cell. The fifth column contains the symbol equals in each cell except for the last, merged cell. The sixth column contains the values 108.09, 8.064, 64.00, and 180.15. There is a thick black line below the number 64.00. The merged cell under the first 5 columns reads molecular mass. To the left of the table is a diagram of a molecule. 6 black spheres are located in a 6-sided ring and connected by alternating double and single black bonds. Attached to each of the 4 black spheres is one smaller white sphere. Attached to the farthest right black sphere is a red sphere connected to 2 more black spheres, all in a row. Attached to the last black sphere of that row are 2 more white spheres. Attached to the first black sphere of that row is another red sphere. A black sphere, attached to 2 red spheres and a white sphere, is attached to the black sphere on the top right of the 6-sided ring. Figure 3.3. The average mass of an aspirin molecule is 180.15 atomic mass units. The model shows the molecular structure of aspirin, C9H8O4. Example 3.1. Computing molecular mass for a covalent compound. Ibuprofen, C13 hydrogen oxide, is a covalent compound and the active ingredient in several popular non-prescription pain medications, such as Advil and Motrin. What is the molecular mass, AMU, for this compound? Solution. Molecules of this compound are composed of 13 carbon atoms, 18 hydrogen atoms, and 2 oxygen atoms. Following the approach described above, the average molecular mass for this compound is therefore, a table is shown that is made up of 6 columns and 5 rows. The header row reads, element, quantity, a blank space, average atomic mass, AMU, a blank space, and subtotal, AMU. The first column contains the symbols C, H, O, and a merged cell. The merged cell runs the length of the first 5 columns. The second column contains the numbers 13, 8, and 2, as well as the merged cell. The third column contains the multiplication symbol in each cell, except for the last, merged cell. The fourth column contains the numbers 12.01, 1.008, and 16.00, as well as the merged cell. The fifth column contains the symbol equals in each cell except for the last merge cell. The sixth column contains the values 156.13, 18.114, 32.00, and 206.27. There is a thick black line below the number 32.00. The merged cell under the first 5 columns reads molecular mass. To the right is a ball and stick model of the structure. At the center, it shows 6 black spheres arranged in a 6-sided ring with alternating double bonds. The 2 black spheres at the top and bottom of the 6-sided ring are each bonded to one smaller white sphere. The black sphere on the left side of the 6-sided ring is connected to another black sphere. This sphere is connected to 2 smaller white spheres and another black sphere. This black sphere is connected to one smaller white sphere and 2 other black spheres. Each of these last 2 black spheres is connected to 2 smaller white spheres. The black sphere on the right side of the 6-sided ring is connected to another black sphere. This black sphere is connected to one smaller white sphere and 2 other black spheres. The black sphere that is connected to it and is situated to the top right is connected to 2 smaller white spheres. The black sphere connected towards the bottom right is connected to 2 red spheres. It forms a double bond with one of these red spheres, and the other red sphere is connected to a smaller white sphere. Check your learning. Acetaminophen, C8H9NO2, is a covalent compound and the active ingredient in several popular non-prescription pain medications, such as Tylenol. What is the molecular mass, AMU, for this compound? Answer: 151.16 atomic mass units. Formula mass for ionic compounds. Ionic compounds are composed of discrete cations and anions, combined in ratios to yield electrically neutral bulk matter. The formula mass for an ionic compound is calculated in the same way as the formula mass for covalent compounds, by summing the average atomic masses of all the atoms in the compound's formula. Keep in mind, however, that the formula for an ionic compound does not represent the composition of a discrete molecule, so it may not correctly be referred to as the molecular mass. As an example, consider sodium chloride. Sodium chloride, the chemical name for common table salt. Sodium chloride is an ionic compound composed of sodium cations, Na+, and chloride anions, Cl-, combined in a 1-to-1 ratio. The formula mass for this compound is computed as 58.44 atomic mass units, see Figure 3.4. A table and diagram are shown. The table is made up of 6 columns and 4 rows. The header row reads element, quantity, a blank space, average atomic mass AMU, a blank space, and subtotal AMU. The first column contains the symbols Na, Cl, and a merged cell. The merged cell runs the length of the first 5 columns. The second column contains the numbers 1 and 1, as well as the merged cell. The third column contains the multiplication symbol in each cell except for the last merged cell. The fourth column contains the numbers 22.99 and 35.45, as well as the merged cell. The fifth column contains the symbol equals in each cell except for the last merged cell. The sixth column contains the values 22.99, 35.45, and 58.44. There is a thick black line below the number 35.45. The merged cell under the first 5 columns reads formula mass. To the left of the table is a diagram of a chemical structure. The diagram shows green and purple spheres placed in an alternating pattern, making up the corners of 8 stacked cubes to form one larger cube. The green spheres are slightly smaller than the purple spheres. Figure 3.4. Table salt sodium chloride contains an array of sodium and chloride ions combined in a 1-to-1 ratio. Its formula mass is 58.44 atomic mass units. Note that the average masses of neutral sodium and chlorine atoms were used in this computation, rather than the masses for sodium cations and chlorine anions. This approach is perfectly acceptable when computing the formula mass of an ionic compound. Even though a sodium cation has a slightly smaller mass than a sodium atom, since it is missing an electron, this difference will be offset by the fact that a chloride anion is slightly more massive than a chloride atom due to the extra electron. Moreover, the mass of an electron is negligibly small with respect to the mass of a typical atom. Even when calculating the mass of an isolated ion, the missing or additional electrons can generally be ignored, since their contribution to the overall mass is negligible, reflected only in the non-significant digits that will be lost when the computed mass is properly rounded. The few exceptions to this guideline are very light ions derived from elements with precisely known atomic masses. Example 3.2. Computing formula mass for an ionic compound. Aluminum sulfate, aluminium sulfate 3, is an ionic compound that is used in the manufacture of paper and in various water purification processes. What is the formula mass, AMU, of this compound? Solution. The formula for this compound indicates it contains Al3+ and SO42- ions combined in a 2:3 ratio. For purposes of computing a formula mass, it is helpful to rewrite the formula in the simpler format Al2-trisulfur dodecoxide. Following the approach outlined above, the formula mass for this compound is calculated as follows. A table is shown that is made up of 6 columns and 5 rows. The header row reads, element, quantity, a blank space, average atomic mass AMU, a blank space, and subtotal AMU. The first column contains the symbols Al, S, O, and a merged cell. The merged cell runs the length of the first 5 columns. The second column contains the numbers 2, 3, and 12, as well as the merged cell. The third column contains the multiplication symbol in each cell except for the last merged cell. The fourth column contains the numbers 26.98, 32.06, and 16.00, as well as the merged cell. The fifth column contains the symbol equals in each cell except for the last merged cell. The sixth column contains the values 53.96, 96.18, 192.00, and 342.14. There is a thick black line under the number 192.00. The merged cell under the first 5 columns reads formula mass. To the right of this table is a ball and stick structure. It shows yellow and gray sphere connected to red spheres in a complex pattern. The yellow and gray spheres are similar in size, but the red spheres appear to be smaller by comparison. Check your learning. Calcium phosphate 2, is an ionic compound and a common anti-caking agent added to food products. What is the formula mass, AMU, of calcium phosphate? Answer: 310.18 atomic mass units. The mole. The identity of a substance is defined not only by the types of atoms or ions it contains, but by the quantity of each type of atom or ion. For example, water, H2O, and hydrogen peroxide, H2O2, are alike in that their respective molecules are composed of hydrogen and oxygen atoms. However, because a hydrogen peroxide molecule contains 2 oxygen atoms, as opposed to the water molecule, which has only 1, the 2 substances exhibit very different properties. Today, sophisticated instruments allow the direct measurement of these defining microscopic traits. However, the same traits were originally derived from the measurement of macroscopic properties, the masses and volumes of bulk quantities of matter, using relatively simple tools, balances and volumetric glassware. This experimental approach required the introduction of a new unit for amount of substances, the mole, which remains indispensable in modern chemical science. The mole is an amount unit similar to familiar units like pair, dozen, gross, etc. It provides a specific measure of the number of atoms or molecules in a sample of matter. One Latin connotation for the word mole is large mass or bulk, which is consistent with its use as the name for this unit. The mole provides a link between an easily measured macroscopic property, bulk mass, and an extremely important fundamental property, number of atoms, molecules, and so forth. A mole of substance is that amount in which there are 6.02214076 times 1023 discrete entities, atoms or molecules. This large number is a fundamental constant known as Avogadro's number, Na, or the Avogadro constant in honor of Italian scientist Amedeo Avogadro. This constant is properly reported with an explicit unit of per mole, a conveniently rounded version being 6.022 times 1023 per mole. Consistent with its definition as an amount unit, 1 mole of any element contains the same number of atoms as 1 mole of any other element. The masses of 1 mole of different elements, however, are different, since the masses of the individual atoms are drastically different. The molar mass of an element, or compound, is the mass in grams of 1 mole of that substance, a property expressed in units of grams per mole, gram per mole. See Figure 3.5. This figure contains 8 different substances displayed on white circles. The amount of each substance is visibly different. Figure 3.5. Each sample contains 6.022 times 1023 atoms, 1.00 moles of atoms. From left to right, top row, 65.4 grams zinc, 12.0 grams carbon, 24.3 grams magnesium, and 63.5 grams copper. From left to right, bottom row, 32.1 grams sulfur, 28.1 grams silicon, 207 grams lead, and 118.7 grams tin. Credit: Modification of work by Mark Ott. The molar mass of any substance is numerically equivalent to its atomic or formula weight in AMU. Per the AMU definition, a single 12C atom weighs 12 atomic mass units. Its atomic mass is 12 atomic mass units. A mole of 12C weighs 12 grams. Its molar mass is 12 grams per mole. This relationship holds for all elements, since their atomic masses are measured relative to that of the AMU reference substance, 12C. Extending this principle, the molar mass of a compound in grams is likewise numerically equivalent to its formula mass in AMU, Figure 3.6. This photo shows 2 vials filled with a colorless liquid. It also shows 2 bowls, one filled with an off-white powder and one filled with a bright red powder. Figure 3.6. Each sample contains 6.02 times 1023 molecules or formula units, 1.00 moles of the compound or element. Clockwise from the upper left, 130.2 grams of C8H17OH, 1 octanol, formula mass 130.2 atomic mass units, 454.4 grams of mercury 2 iodide, formula mass 454.4 atomic mass units, 32.0 grams of CH3OH methanol, formula mass 32.0 atomic mass units, and 256. Credit: Sahar Atwa. Element average atomic mass, AMU, molar mass, gram per mole, atoms, mole, C 12.01, 12.01, 6.02, 2 times 1023, H 1.008, 1.008, 6.022 times 1023, O 16.00, 16.00, 6.022 times 1023, Naha 22.99, 22.99, 6.02, 2 times 1023, CL 35.45, 35.45, 6.022 times 1023. While atomic mass and molar mass are numerically equivalent, keep in mind that they are vastly different in terms of scale, as represented by the vast difference in the magnitudes of their respective units, AMU versus G. To appreciate the enormity of the mole, consider a small drop of water weighing about 0.03 grams, see Figure 3.7. Although this represents just a tiny fraction of 1 mole of water, approximately 18 grams, it contains more water molecules than can be clearly imagined. If the molecules were distributed equally among the roughly 7 billion people on Earth, each person would receive more than 100 billion molecules. A close-up photo of a water droplet on a leaf is shown. The water droplet is not perfectly spherical. Figure 3.7. The number of molecules in a single droplet of water is roughly 100 billion times greater than the number of people on Earth. Credit Tanakahu /Wikimedia Commons. Link to learning. The mole is used in chemistry to represent 6.022 times 1023 of something, but it can be difficult to conceptualize such a large number. Watch this video and then complete the think questions that follow. Explore more about the mole by reviewing the information under Dig Deeper. The relationships between formula mass, the mole, and Avogadro's number can be applied to compute various quantities that describe the composition of substances and compounds, as demonstrated in the next several example problems. Example 3.3. Deriving moles from grams for an element. According to nutritional guidelines from the U.S. Department of Agriculture, the estimated average requirement for dietary potassium is 4.7 grams. What is the estimated average requirement of potassium in moles? Solution. The mass of K is provided, and the corresponding amount of K in moles is requested. Referring to the periodic table, the atomic mass of K is 39.10 atomic mass units, and so its molar mass is 39.10 grams per mole. The given mass of K, 4.7 grams, is a bit more than 1/10 the molar mass, 39.10 grams, so a reasonable ballpark estimate of the number of moles would be slightly greater than 0.1 moles. The molar amount of a substance may be calculated by dividing its mass, g, by its molar mass, gram per mole. A diagram of two boxes connected by a right-facing arrow is shown. The box on the left contains the phrase mass of K atoms, g, while the one on the right contains the phrase moles of K atoms, mole. There is a phrase under the arrow that says divide by molar mass, gram per mole. The factor label method supports this mathematical approach since the unit g cancels and the answer has units of mole. 4.7 g K mole K 39.10 grams K equals 0.12 moles K. The calculated magnitude, 0.12 moles K, is consistent with our ballpark expectation since it is a bit greater than. Check your learning. Beryllium is a light metal used to fabricate transparent X-ray windows for medical imaging instruments. How many moles of B are in a tinfoil window weighing 3.24 grams? Answer: 0.360 moles. Example 3.4. Deriving grams from moles for an element. A liter of air contains 9.2 times 10⁻⁴ moles argon. What is the mass of Ar in a liter of air? Solution. The molar amount of Ar is provided and must be used to derive the corresponding mass in grams. Since the amount of Ar is less than 1 mole, the mass will be less than the mass of 1 mole of Ar, approximately 40 grams. The molar amount in question is approximately 1/1000th, approximately 10⁻³ of a mole, and so the corresponding mass should be roughly 1/1000th of the molar mass, approximately 0.04 grams. A diagram of two boxes connected by a right-facing arrow is shown. The box on the left contains the phrase moles of Ar atoms, mole, while the one on the right contains the phrase mass of Ar atoms, g. There is a phrase under the arrow that says multiply by molar mass, gram per mole. In this case, logic dictates, and the factor label method supports, multiplying the provided amount, mole by the molar mass, gram per mole. 9.2 times 10⁻⁴ molar, 39.95 grams R-molar, equals 0.037 grams Ar. The result is in agreement with our expectations, around 0.04 grams Ar. Check your learning. What is the mass of 2.561 moles of gold? Answer: 504.5 grams. Example 3.5. Deriving number of atoms from mass for an element. Copper is commonly used to fabricate electrical wire, figure 3.8. How many copper atoms are in 5.00 grams of copper wire? A close-up photo of a spool of copper wire is shown. Figure 3.8 copper wire is composed of many atoms of Cu. Credit Emilian Robert Vickel. Solution. The number of Cu atoms in the wire may be conveniently derived from its mass by a two-step computation, first calculating the molar amount of Cu and then using Avogadro's number, Na, to convert this molar amount to number of Cu atoms. A diagram of three boxes connected by a right-facing arrow in between each is shown. The box on the left contains the phrase mass of Cu atoms, G. The middle box reads moles of Cu atoms, mol, while the one on the right contains the phrase number of Cu atoms. There is a phrase under the left arrow that says divide by molar mass, gram per mole, and under the right arrow it states multiply by Avogadro's number, mole superscript -1. Considering that the provided sample mass, 5.00 grams, is a little less than 1/10 the mass of 1 mole of Cu, approximately 64 G, a reasonable estimate for the number of atoms in the sample would be on the order of 1/10 Na, or approximately 1022 Cu. Carrying out the two-step computation yields 5.00 GCu mole Cu 63.55 grams, Cu 6.02 2 times 1023 Cu atoms mole Cu equals 4.74 times 1022 Cu atoms. The factor label method yields the desired cancellation of units, and the computed result is on the order of 1022 as expected. Check your learning. A prospector panning for gold in a river collects 15.00 grams of pure gold. How many Au atoms are in this quantity of gold? Answer: 4.58, 6 times 1022 atom mass. Example 3.6. Deriving moles from grams for a compound. Our bodies synthesize protein from amino acids. One of these amino acids is glycine, which has the molecular formula C2H5O2N. How many moles of glycine molecules are contained in 28.35 grams of glycine? Solution: derive the number of moles of a compound from its mass following the same procedure used for an element in example 3.3. A diagram of two boxes connected by a right-facing arrow is shown. The box on the left contains the phrase mass of C subscript 2H subscript 50 subscript 2N G, while the box on the right contains the phrase moles of C subscript 2H subscript 2H subscript 50 subscript 2N mole. There is a phrase under the arrow that says divide by molar mass, gram per mole. The molar mass of glycine is required for this calculation, and it is computed in the same fashion as its molecular mass. 1 mole of glycine, C2H5O2N, contains 2 moles of carbon, 5 moles of hydrogen, 2 moles of oxygen, and 1 mole of nitrogen. A table is shown that is made up of 6 columns and 6 rows. The header row reads element, quantity, mole element per mole compound, a blank space, molar mass, gram per mole element, a blank space, and subtotal AMU. The first column contains the symbols C, H, O, N, and a merged cell. The merged cell runs the width of the first 5 columns. The second column contains the numbers 2, 5, 2, and 1, as well as the merged cell. The third column contains the multiplication symbol in each cell except for the last, merged cell. The fourth column contains the numbers 12.01, 1.008, 16.00, and 14.007, as well as the merged cell. The fifth column contains the symbol equals in each cell except for the last, merged cell. The sixth column contains the values 24.02, 5.040, 32.00, 14.007, and 75.07. There is a thick black line under the number 14.007. The merged cell under the first 5 columns reads molar mass, gram per mole compound. There is a ball and stick drawing to the right of this table. It shows a black sphere that forms a double bond with a slightly smaller red sphere, a single bond with another red sphere, and a single bond with another black sphere. The red sphere that forms a single bond with the black sphere also forms a single bond with a smaller white sphere. The second black sphere forms a single bond with a smaller white sphere and a smaller blue sphere. The blue sphere forms a single bond with two smaller, white spheres each. The provided mass of glycine, approximately 28 g, is a bit more than 1/3 the molar mass, approximately 75 grams per mole, so the computed result is expected to be a bit greater than 1/3 of a mole, approximately 0.33 moles. Dividing the compound's mass by its molar mass yields 28.35 glycine, mole glycine, 75.07 grams glycine equals 0.378 moles glycine. This result is consistent with the rough estimate. Check your learning. How many moles of sucrose, C12 hydrogen oxide, are in a 25-gram sample of sucrose? Answer: 0.073 moles. Example 3.7. Deriving grams from moles for a compound. Vitamin C is a covalent compound with the molecular formula C6H8O6. The recommended daily dietary allowance of vitamin C for children aged 4 to 8 years is 1.42 times 10⁻⁴ moles. What is the mass of this allowance in grams? Solution. As for elements, the mass of a compound can be derived from its molar amount, as shown. A diagram of two boxes connected by a right-facing arrow is shown. The box on the left contains the phrase moles of vitamin C, mole, while the one on the right contains the phrase mass of vitamin C, g. There is a phrase under the arrow that says multiply by molar mass, gram per mole. The molar mass for this compound is computed to be 176.124 grams per mole. The given number of moles is a very small fraction of a mole, approximately 10⁻⁴ or 1/10,000th. Therefore, the corresponding mass is expected to be about 1/10,000th of the molar mass, approximately 0.02 grams. Performing the calculation yields 1.42 times 10⁻⁴ mole vitamin C, 176.124 grams vitamin C mole vitamin C equals 0.0250 grams vitamin C. This is consistent with the anticipated result. Check your learning. What is the mass of 0.443 moles of hydrazine, N2H4? Answer: 14.2 grams. Example 3.8. Deriving the number of atoms and molecules from the mass of a compound. A packet of an artificial sweetener contains 40.0 milligrams of saccharin, C7H5NO3S, which has the structural formula. A diagram of a molecule is shown that is made up of two ring structures attached together. The left ring is hexagonal in shape with C atoms at each point of the ring and alternating single and double bonds. A double bond occurs between the C atom at the top vertex of the hexagon and the C atom down and to the left of it. The C atoms on the left top and bottom of the structure form a single bond to an H atom each. The two right C atoms make up one side of a pentagon, and the other points of the pentagon are made up of a C atom, an N atom, and an S atom if read clockwise. The C atom forms a double bond with an O atom. The N atom forms a single bond with an H atom. The S atom forms two double bonds to two O atoms. Given that saccharin has a molar mass of 183.18 grams per mole, how many saccharin molecules are in a 40.0 milligrams, 0.0400 grams sample of saccharin? How many carbon atoms are in the same sample? Solution. The number of molecules in a given mass of compound is computed by first deriving the number of moles, as demonstrated in example 3.6, and then multiplying by Avogadro's number. A diagram of three boxes connected by a right-facing arrow in between each is shown. The box on the left contains the phrase mass of C subscript 7H subscript 5 NO subscript 3S G. The middle box reads moles of C subscript 7H subscript 5 NO subscript 3S subscript 3S mole, while the one on the right contains the phrase number of C subscript 7H subscript 5 NO subscript 3S molecules. There is a phrase under the left arrow that says divide by molar mass, gram per mole, and under the right arrow it states multiply by Avogadro's number. using the provided mass and molar mass for saccharin yields 0.0400 Gc7H5NO3S183.18 Gc7H5NO3S molecules, 1.31 times 1020 C7H5NO3S molecule. The compound's formula shows that each molecule contains 7 carbon atoms, and so the number of C atoms in the provided sample is 1.31 times 1020 C7H5NO3S molecules, 7 C atoms, 1 C7H5NO3S molecule equals 9.17 times 1020 C atoms. Check your learning. How many tetracarbon decahydride molecules are contained in 9.213 grams of this compound? How many hydrogen atoms? Answer: 9.545 times 1022 molecules. C4H10, 9.545 times 1023 atoms H. How sciences interconnect. Counting neurotransmitter molecules in the brain. The brain is the control center of the central nervous system, figure 3.9. It sends and receives signals to and from muscles and other internal organs to monitor and control their functions. It processes stimuli detected by sensory organs to guide interactions with the external world. And it houses the complex physiological processes that give rise to our intellect and emotions. The broad field of neuroscience spans all aspects of the structure and function of the central nervous system, including research on the anatomy and physiology of the brain. Great progress has been made in brain research over the past few decades, and the BRAIN Initiative, a federal initiative announced in 2013, aims to accelerate and capitalize on these advances through the concerted efforts of various industrial, academic, and government agencies. More details available at www.whitehouse.gov/share/brain-initiative. Two pictures are shown. The left picture shows the human brain. The right picture is a microscopic image that depicts two large, irregularly shaped masses in a field of thread-like material interspersed with smaller, relatively round masses. The two larger masses are labeled with arrows and the phrase neuron cells. Figure 3.9a, a typical human brain weighs about 1.5 kilograms and occupies a volume of roughly 1.1 L. B. Information is transmitted in brain tissue and throughout the central nervous system by specialized cells called neurons. Micrograph shows cells at 1600 times magnification. Specialized cells called neurons transmit information between different parts of the central nervous system by way of electrical and chemical signals. Chemical signaling occurs at the interface between different neurons when one of the cells releases molecules, called neurotransmitters, that diffuse across the small gap between the cells, called the synapse, and bind to the surface of the other cell. These neurotransmitter molecules are stored in small intracellular structures called vesicles that fuse to the cell membrane and then break open to release their contents when the neuron is appropriately stimulated. This process is called exocytosis. See figure 3.10. One neurotransmitter that has been very extensively studied is dopamine, C8H11 nitrogen dioxide. Dopamine is involved in various neurological processes that impact a wide variety of human behaviors. Dysfunctions in the dopamine systems of the brain underlie serious neurological diseases such as Parkinson's and schizophrenia. Two diagrams are shown. In the upper left corner of the left diagram, an oval with a darkened center that has 5 short branching appendages and 1 long tail-like appendage is shown and connected by an arrow to another image. This image depicts a close-up view of the oval section and its interaction with the tail-like portion of a similar structure. The close-up view is composed of a narrow tube labeled neuron leading down to a bulbous base that holds 13 circles filled with small dots. These circles are labeled vesicles. The base of the bulbous structure is next to a curved object labeled neuron, and very small dots are emerging from the bulb's base and flowing toward the curved structure. The gap in between the two structures is labeled synapse, and the small dots are labeled neurotransmitters. The diagram on the right depicts a molecule composed of 6 black spheres connected by alternating double and single bonds in a hexagonal ring with other spheres attached to it. 3 of the black spheres are connected to 1 smaller white sphere each. Two of the black balls are connected to a smaller red sphere each. Each red sphere is connected to a smaller white sphere. One black sphere is connected to another black sphere. It is connected to two smaller white spheres and another black sphere. This second black sphere is connected to two smaller white spheres and a slightly smaller blue sphere. The blue sphere is connected to two smaller white spheres. Figure 3.10a. Chemical signals are transmitted from neurons to other cells by the release of neurotransmitter molecules into the small gaps, synapses between the cells. B. Dopamine, C8H11NO2, is a neurotransmitter involved in a number of neurological processes. One important aspect of the complex processes related to dopamine signaling is the number of neurotransmitter molecules released during exocytosis. Since this number is a central factor in determining neurological response and subsequent human thought and action, it is important to know how this number changes with certain controlled stimulations, such as the administration of drugs. It is also important to understand the mechanism responsible for any changes in the number of neurotransmitter molecules released. For example, some dysfunction in exocytosis, a change in the number of vesicles in the neuron, or a change in the number of neurotransmitter molecules in each vesicle. Significant progress has been made recently in directly measuring the number of dopamine molecules stored in individual vesicles and the amount actually released when the vesicle undergoes exocytosis. Using miniaturized probes that can selectively detect dopamine molecules in very small amounts, scientists have determined that the vesicles of a certain type of mouse brain neuron contain an average of 30,000 dopamine molecules per vesicle, about 5 × 10⁻20 mol or 50 Z-mol. Analysis of these neurons from mice subjected to various drug therapies shows significant changes in the average number of dopamine molecules contained in individual vesicles, increasing or decreasing by up to 3-fold, depending on the specific drug used. These studies also indicate that not all of the dopamine in a given vesicle is released during exocytosis, suggesting that it may be possible to regulate the fraction released using pharmaceutical therapies. 1. Learning objectives. By the end of this section, you will be able to compute the percent composition of a compound, determine the empirical formula of a compound, determine the molecular formula of a compound. The previous section discussed the relationship between the bulk mass of a substance and the number of atoms or molecules it contains, moles. Given the chemical formula of the substance, one may determine the amount of the substance, moles, from its mass, and vice versa. But what if the chemical formula of a substance is unknown? In this section, these same principles will be applied to derive the chemical formulas of unknown substances from experimental mass measurements. Percent composition. The elemental makeup of a compound defines its chemical identity, and chemical formulas are the most succinct way of representing this elemental makeup. When a compound's formula is unknown, measuring the mass of each of its constituent elements is often the first step in the process of determining the formula experimentally. The results of these measurements permit the calculation of the compound's percent composition, defined as the percentage by mass of each element in the compound. For example, consider a gaseous compound composed solely of carbon and hydrogen. The percent composition of this compound could be represented as follows. Percent H equals mass H mass compound times 100%. Percent C equals mass C mass compound times 100%. If analysis of a 10.0 gram sample of this gas showed it to contain 2.5 grams H and 7.5 grams C, the percent composition would be calculated to be 25% H and 75% C. Percent H equals 2.5 grams H, 10.0 grams compound, times 100% equals 25%. Percent C equals 7.5 grams C, 10.0 grams compound times 100% equals 75%. Example 3.9. Calculation of percent composition. Analysis of a 12.04 gram sample of a liquid compound composed of carbon, hydrogen, and nitrogen showed it to contain 7.34 grams C, 1.85 grams H, and 2.85 grams N. What is the percent composition of this compound? Solution. To calculate percent composition, divide the experimentally derived mass of each element by the overall mass of the compound, and then convert to a percentage. Percent C equals 7.34 grams C, 12.04 grams compound times 100% equals 61.0% H equals 1.85 grams H 12.04 grams. Compound times 100% equals 15.4% N equals 2.85 grams N 12.04 grams compound times 100% equals 23.7%. The analysis results indicate that the compound is 61.0% C, 15.4% H, and 23.7% N by mass. Check your learning. A 24.81 gram sample of a gaseous compound containing only carbon, oxygen, and chlorine is determined to contain 3.01 grams C, 4.00 grams O, and 17.81 grams Cl. What is this compound's percent composition? Answer: 12.1% C, 16.1% O, 71.79% Cl. Determining percent composition from molecular or empirical formulas. Percent composition is also useful for evaluating the relative abundance of a given element in different compounds of known formulas. As one example, consider the common nitrogen-containing fertilizers ammonia, NH3, ammonium nitrate, NH4NO3, and urea, CH4N2O. The element nitrogen is the active ingredient for agricultural purposes, so the mass percentage of nitrogen in the compound is a practical and economic concern for consumers choosing among these fertilizers. For these sorts of applications, the percent composition of a compound is easily derived from its formula mass and the atomic masses of its constituent elements. A molecule of NH3 contains one N atom weighing 14.01 atomic mass units and 3 H atoms weighing a total of 3 times 1.008 atomic mass units equals 3.024 atomic mass units. The formula mass of ammonia is therefore 14.01 atomic mass units plus 3.024 atomic mass units equals 17.03 atomic mass units, and its percent composition is %N equals 14.01 atomic mass units, N 17.03 AMUNH 3 times 100% equals 82.27%, H equals 3.03 AMUNH 3 times 100% equals 17. This same approach may be taken considering a pair of molecules, a dozen molecules, or a mole of molecules, etc. The latter amount is most convenient and would simply involve the use of molar masses instead of atomic and formula masses, as demonstrated, example 3.10. As long as the molecular or empirical formula of the compound in question is known, the percent composition may be derived from the atomic or molar masses of the compound's elements. Example 3.10. Determining percent composition from a molecular formula. Aspirin is a compound with the molecular formula C9H8O4. What is its percent composition? Solution. To calculate the percent composition, the masses of C, H, and O and a known mass of C9H8O4 are needed. It is convenient to consider 1 mole of C9H8O4 and use its molar mass, 180.159 grams per mole, determined from the chemical formula, to calculate the percentages of each of its elements. Percent C equals 9 moles C times molar mass C molar. Mass C9H8O4 times 100 equals 9 times 12.0, 1 grams per mole, 180.159 grams per mole times 100 equals 108.09 grams per mole, 180.159 grams per mole times 100% C equals 60.00% C. Percent H equals 8 moles H times molar mass H molar dot mass C 9 H8O4 times 100 equals 8 times 1.008 grams per mole, 180.159 grams per mole times 100 equals 8.064 grams per mole, 180.159 grams per mole times 100% H equals 4.476% H. Percent O equals 4 moles, O times molar mass, O molar dot mass C, 9 H8O4 times 100 equals 4 times 16.00 grams per mole, 180.159 grams per mole times 100 equals 64.00 grams per mole, 180.159 grams per mole times 100% O equals 35.52%. Note that these percentages sum to equal 100.00% when appropriately rounded. Check your learning. To 3 significant digits, what is the mass percentage of iron in the compound iron 3 oxide? Answer: 69.9% Fe. Determination of empirical formulas. As previously mentioned, the most common approach to determining a compound's chemical formula is to first measure the masses of its constituent elements. However, keep in mind that chemical formulas represent the relative numbers, not masses, of atoms in the substance. Therefore, any experimentally derived data involving mass must be used to derive the corresponding numbers of atoms in the compound. This is accomplished using molar masses to convert the mass of each element to a number of moles. These molar amounts are used to compute whole number ratios that can be used to derive the empirical formula of the substance. Consider a sample of compound determined to contain 1.71 grams C and 0.287 grams H. The corresponding numbers of atoms in moles are 1.7, 1 gram C times 1 mole C, 12.0, 1 gram C equals 0.142 moles, C 0.287 grams H times 1 mole H, 1.008 grams H equals 0.284 moles H. Thus, this compound may be represented by the formula C 0.1428. Per convention, formulas contain whole number subscripts, which can be achieved by dividing each subscript by the smaller subscript. C 0.142, 0.142, H 0.2, 840.142, or CH2. Recall that subscripts of 1 are not written, but rather assumed if no other number is present. The empirical formula for this compound is thus CH2. This may or may not be the compound's molecular formula as well. However, additional information is needed to make that determination, as discussed later in this section. Consider as another example a sample of compound determined to contain 5.31 grams Cl and 8.40 grams O. Following the same approach yields a tentative empirical formula of Cl 0.150 O 0.525 equals Cl 0.150 0.150 O 0.150 150 equals chlorine trioxide 0.5. In this case, dividing by the smallest subscript still leaves us with a decimal subscript in the empirical formula. To convert this into a whole number, multiply each of the subscripts by 2, retaining the same atom ratio and yielding dichlorine heptoxide as the final empirical formula. In summary, empirical formulas are derived from experimentally measured element masses by deriving the number of moles of each element from its mass, dividing each element's molar amount by the smallest molar amount to yield subscripts for a tentative empirical formula, multiplying all coefficients by an integer if necessary to ensure that the smallest whole number ratio of subscripts is obtained. Figure 3.11 outlines this procedure in flowchart fashion for a substance containing elements A and X. 2 rounded smooth black stones are shown. Figure 3.12 hematite is an iron oxide that is used in jewelry. Credit Mauro Kateb. Solution. This problem provides the mass in grams of each element. Begin by finding the moles of each. 34.97 grams Fe, mole Fe 55.85 grams, 15.03 grams, O mole O 16.00 grams, equals 0.6261 moles Fe 0.9394 moles O. Next, derive the iron to oxygen molar ratio by dividing by the lesser number of moles. 0.6261 equals 1.000 moles of iron to 1. Finally, multiply the ratio by 2 to get the smallest possible whole number subscripts while still maintaining the correct iron to oxygen ratio. 2 iron 2 oxide 0.5 equals iron 3 oxide. The empirical formula is iron 3 oxide. Check your learning. What is the empirical formula of a compound if a sample contains 0.130 grams of nitrogen and 0.370 grams of oxygen? Answer: N2O5. Link to learning. For additional worked examples illustrating the derivation of empirical formulas, watch the brief video clip, Deriving Empirical Formulas from Percent Composition. Finally, with regard to deriving empirical formulas, consider instances in which a compound's percent composition is available rather than the absolute masses of the compound's constituent elements. In such cases, the percent composition can be used to calculate the masses of elements present in any convenient mass of compound. These masses can then be used to derive the empirical formula in the usual fashion. Example 3.12. Determining an empirical formula from percent composition. The bacterial fermentation of grain to produce ethanol forms a gas with a percent composition of 27.29% C and 72.71% O, figure 3.13. What is the empirical formula for this gas? A picture is shown of 4 copper-colored industrial containers with a large pipe connecting to the top of each one. Figure 3.13. An oxide of carbon is removed from these fermentation tanks through the large copper pipes at the top. Credit /Wikimedia Commons. Solution. Since the scale for percentages is 100, it is most convenient to calculate the mass of elements present in a sample weighing 100 grams. The calculation is most convenient because, per the definition for percent composition, the mass of a given element in grams is numerically equivalent to the element's mass percentage. This numerical equivalence results from the definition of the percentage unit, whose name is derived from the Latin phrase percentum, meaning by the hundred. Considering this definition, the mass percentages provided may be more conveniently expressed as fractions. 27.29% C 72.71% O equals 27.29 grams C 100G compound, 72.71 grams O 100G compound. The molar amounts of carbon and oxygen in a 100-gram sample are calculated by dividing each element's mass by its molar mass. 27.29 grams C, mole C 12.01 grams, 2.71 grams O, mole 16.00 grams, equals 2.272 moles, C 4.544 moles O. Coefficients for the tentative empirical formula are derived by 2.272 moles C, 2.272 equals 14.544 moles, O, 2.272 equals 2. Since the resulting ratio is 1 carbon to 2 oxygen atoms, the empirical formula is CO2. Check your learning. What is the empirical formula of a compound containing 40.0% C, 6.71% H, and 53.28% O? Answer: CH2O. Derivation of molecular formulas. Recall that empirical formulas are symbols representing the relative numbers of a compound's elements. Determining the absolute numbers of atoms that compose a single molecule of a covalent compound requires knowledge of both its empirical formula and its molecular mass or molar mass. These quantities may be determined experimentally by various measurement techniques. Molecular mass, for example, is often derived from the mass spectrum of the compound. See discussion of this technique in the previous chapter on atoms and molecules. Molar mass can be measured by a number of experimental methods, many of which will be introduced in later chapters of this text. Molecular formulas are derived by comparing the compound's molecular or molar mass to its empirical formula mass. As the name suggests, an empirical formula mass is the sum of the average atomic masses of all the atoms represented in an empirical formula. If the molecular or molar mass of the substance is known, it may be divided by the empirical formula mass to yield the number of empirical formula units per molecule, N. Molecular or molar mass AMU orgmole, empirical formula mass AMU orgmole equals N formula units/molecule. The molecular formula is then obtained by multiplying each subscript in the empirical formula by N, as shown by the generic empirical formula AXB equals NXBNY. For example, consider a covalent compound whose empirical formula is determined to be CH2O. The empirical formula mass for this compound is approximately 30 atomic mass units. The sum of 12 atomic mass units for one C atom, 2 atomic mass units for 2 H atoms, and 16 atomic mass units for one O atom. If the compound's molecular mass is determined to be 180 atomic mass units, this indicates that molecules of this compound contain 6 times the number of atoms represented in the empirical formula. 180 atomic mass units / molecule 30 mu formula unit equals 6 formula units / molecule. Molecules of this compound are then represented by molecular formulas whose subscripts are 6 times greater than those in the empirical formula. CH2O 6 equals C6 hydrogen oxide. Note that this same approach may be used when the molar mass, gram per mole, instead of the molecular mass, AMU, is used. In this case, 1 mole of empirical formula units and molecules is considered, as opposed to single units and molecules. Example 3.13. Determination of the molecular formula for nicotine. Nicotine, an alkaloid in the nightshade family of plants that is mainly responsible for the addictive nature of cigarettes, contains 74.02% C, 8.710% H, and 17.27% N. If 40.57 grams of nicotine contains 0.2500 moles nicotine, what is the molecular formula? Solution. Determining the molecular formula from the provided data will require comparison of the compound's empirical formula mass to its molar mass. As the first step, use the percent composition to derive the compound's empirical formula. Assuming a convenient, a 100-gram sample of nicotine yields the following molar amounts of its elements: 74.02 grams C, 1 mole C, 12.01 grams C, 8.710 grams H, 1 mole H, 1.008 grams H, 17.27 grams N, 1 mole N, 14.01 grams N, equals 641 moles H, 1.233 moles, 8.641 mole H / 1.233 mole N equals 7. 1.233 mole N / 1.233 mole N equals 1. 1.233, 1.233, 6.163, 1.233, 8.6, 24, 1.233 equals 1.000 moles N, 4.998 moles C, 6.994 moles H. The C to N and H to N molar ratios are adequately close to whole numbers, and so the empirical formula is C5H7N. The empirical formula mass for this compound is therefore 81.13 atomic mass units / formula unit, or 81.13 grams per mole formula unit. Calculate the molar mass for nicotine from the given mass and molar amount of compound. 40.57 grams nicotine, 0.2500 moles nicotine equals 162.3 gmol. Comparing the molar mass and empirical formula mass indicates that each nicotine molecule contains 2 formula units. 162.3 grams per mole, 81.13 G formula unit equals 2 formula units / molecule. Finally, derive the molecular formula for nicotine from the empirical formula by multiplying each subscript by 2. C5H7N, 2 equals C10 hydrogen nitride. Check your learning. What is the molecular formula of a compound with a percent composition of 49.47% C, 5.201% H, 28.84% N, and 16.48% O, and a molecular mass of 194.2 atomic mass units? Answer: C8H10 tetranitrogen dioxide. Learning objectives. By the end of this section, you will be able to describe the fundamental properties of solutions, calculate solution concentrations using molarity, perform dilution calculations using the dilution equation. Preceding sections of this chapter focused on the composition of substances, samples of matter that contain only one type of element or compound. However, mixtures, samples of matter containing 2 or more substances physically combined, are more commonly encountered in nature than are pure substances. Similar to a pure substance, the relative composition of a mixture plays an important role in determining its properties. The relative amount of oxygen in a planet's atmosphere determines its ability to sustain aerobic life, The relative amount of iron, carbon, nickel, and other elements in steel, a mixture known as an alloy, determine its physical strength and resistance to corrosion. The relative amount of the active ingredient in a medicine determines its effectiveness in achieving the desired pharmacological effect. The relative amount of sugar in a beverage determines its sweetness. See Figure 3.14. This section will describe one of the most common ways in which the relative compositions of mixtures may be quantified. A picture is shown of sugar being poured from a spoon into a cup. Figure 3.14 sugar is one of many components in the complex mixture known as coffee. The amount of sugar in a given amount of coffee is an important determinant of the beverage's sweetness. Credit: Jane Whitney. Solutions. Solutions have previously been defined as homogeneous mixtures, meaning that the composition of the mixture, and therefore its properties, is uniform throughout its entire volume. Solutions occur frequently in nature and have also been implemented in many forms of man-made technology. A more thorough treatment of solution properties is provided in the chapter on solutions and colloids, but provided here is an introduction to some of the basic properties of solutions. The relative amount of a given solution component is known as its concentration. Often, though not always, a solution contains one component with a concentration that is significantly greater than that of all other components. This component is called the solvent and may be viewed as the medium in which the other components are dispersed or dissolved. Solutions in which water is the solvent are, of course, very common on our planet. A solution in which water is the solvent is called an aqueous solution. A solute is a component of a solution that is typically present at a much lower concentration than the solvent. Solute concentrations are often described with qualitative terms such as dilute of relatively low concentration and concentrated of relatively high concentration. Concentrations may be quantitatively assessed using a wide variety of measurement units, each convenient for particular applications. Molarity M is a useful concentration unit for many applications in chemistry. Molarity is defined as the number of moles of solute in exactly 1 liter, 1 L of the solution. M equals mole solute L solution. Example 3.14. Calculating molar concentrations. A 355 milliliter soft drink sample contains 0.133 moles of sucrose, table sugar. What is the molar concentration of sucrose in the beverage? Solution. Since the molar amount of solute and the volume of solution are both given, the molarity can be calculated using the definition of molarity. Per this definition, the solution volume must be converted from ml to L. M equals mole solute L solution equals 0.133 moles, 355 milliliters, times 1L, 1000 ml equals 0.375 m. Check your learning. A teaspoon of table sugar contains about 0.01 moles sucrose. What is the molarity of sucrose if a teaspoon of sugar has been dissolved in a cup of tea with a volume of 200 milliliters? Answer: 0.05 m. Example 3.15. Deriving moles and volumes from molar concentrations. How much sugar, mol, is contained in a modest sip, approximately 10 milliliters, of the soft drink from example 3.14? Solution. Rearrange the definition of molarity to isolate the quantity sought, moles of sugar, then substitute the value for molarity derived in example 3.14, 0.375 m. M equals mole solid L solution mole solid equals M times L solution mole solid equals 0.375 moles. Sugar L times 10 milliliters times 1L 1000 ml equals 0.0. Check your learning. What volume, frial of the sweetened tea described in example 3.14 contains the same amount of sugar mol as 10 milliliters of the soft drink in this example? Answer: 80 milliliters. Example 3.16. Calculating molar concentrations from the mass of solute. Distilled white vinegar, figure 3.15, is a solution of acetic acid, CH3CO2H, in water. A 0.500 L vinegar solution contains 25.2 grams of acetic acid. What is the concentration of the acetic acid solution in units of molarity? A label on a container is shown. The label has a picture of a salad with the words distilled white vinegar and reduced with water to 5% acidity written above it. Figure 3.15. Distilled white vinegar is a solution of acetic acid in water. Solution. As in previous examples, the definition of molarity is the primary equation used to calculate the quantity sought. Since the mass of solute is provided instead of its molar amount, use the solute's molar mass to obtain the amount of solute in moles. M equals moles solid L solution equals 25.2 GCH3, Colorado 2H times 1 mole CH3CO2H6, 0.052 grams, CH3CO2H 0.839 m. Calculate the molarity of 6.52 grams of cobalt-2 chloride, 128.9 Answer: 0.674 m. Example 3.17. Determining the mass of solute in a given volume of solution. How many grams of sodium chloride are contained in 0.250 L of a 5.30 m solution? Solution. The volume and molarity of the solution are specified, so the amount M11L solute is easily computed as demonstrated in example 3.15. M equals mole solute equals M times L solution mole solute equals 5.30 moles, NaCl times 0.250 L equals 1.325 moles sodium chloride. Check your learning. How many grams of calcium? Answer: 5.55 grams calcium chloride. When performing calculations stepwise, as in example 3.17, it is important to refrain from rounding any intermediate calculation results, which can lead to rounding errors in the final result. In example 3.17, the molar amount of sodium chloride computed in the first step, 1.325 moles, would be properly rounded to 1.32 moles if it were to be reported. However, although the last digit, 5, is not significant, it must be retained as a guard digit in the intermediate calculation. If the guard digit had not been retained, the final calculation for the mass of sodium chloride would have been 77.1 grams, a difference of 0.3 grams. In addition to retaining a guard digit for intermediate calculations, rounding errors may also be avoided by performing computations in a single step. See example 3.18. This eliminates intermediate steps so that only the final result is rounded. Example 3.18. Determining the volume of solution containing a given mass of solute. In example 3.16, the concentration of acetic acid in white vinegar was determined to be 0.839 m. What volume of vinegar contains 75.6 grams of acetic acid? Solution. First, use the molar mass to calculate moles of acetic acid from the given mass. G solute times mole solute solute equals mole solute. Then use the molarity of the solution to calculate the volume of solution containing this molar amount of solute. Combining these two steps into one yields. Combining these two steps into one yields. Combining these two steps into one yields. This is 0.6 equals 1.5. Answer: 0.370 L. Dilution of solutions. Dilution is the process whereby the concentration of a solution is lessened by the addition of solvent. For example, a glass of iced tea becomes increasingly diluted as the ice melts. The water from the melting ice increases the volume of the solvent, water, and the overall volume of the solution, iced tea, thereby reducing the relative concentrations of the solutes that give the beverage its taste. Figure 3.16. This figure shows two graduated cylinders side by side. The first has about half as much blue liquid as the second. The blue liquid is darker in the first cylinder than in the second. Figure 3.16. Both solutions contain the same mass of copper nitrate. The solution on the right is more dilute because the copper nitrate is dissolved in more solvent. Credit: Marcotte. Dilution is also a common means of preparing solutions of a desired concentration. By adding solvent to a measured portion of a more concentrated stock solution, a solution of lesser concentration may be prepared. For example, commercial pesticides are typically sold as solutions in which the active ingredients are far more concentrated than is appropriate for their application. Before they can be used on crops, the pesticides must be diluted. This is also a very common practice for the preparation of a number of common laboratory reagents. A simple mathematical relationship can be used to relate the volumes and concentrations of a solution before and after the dilution process. According to the definition of molarity, the number of moles of solute in a solution N is equal to the product of the solution's molarity M and its volume in liters, L. N equals ml. Expressions like these may be written for a solution before and after it is diluted. N1 equals M1L1, N2 equals M2L2, where the subscripts 1 and 2 refer to the solution before and after the dilution, respectively. Since the dilution process does not change the amount of solute in the solution, N1 equals N2. Thus, these two equations may be set equal to one another. M1L1 equals M2L2. This relation is commonly referred to as the dilution equation. Although this equation uses molarity as the unit of concentration and liters as the unit of volume, other units of concentration and volume may be used as long as the units properly cancel per the factor label method. Reflecting this versatility, the dilution equation is often written in the more general form. C1V1 equals C2V2, where C and V are concentration and volume respectively. Link to learning. Use the simulation to explore the relations between solute amount, solution volume, and concentration, and to confirm the dilution equation. Example 3.19. Determining the concentration of a diluted solution. If 0.850 L of a 5.00 M solution of copper nitrate, copper 1 nitrate 2, is diluted to a volume of 1.80 L by the addition of water, what is the molarity of the diluted solution? Solution. The stock concentration C1 and volume V1 are provided, as well as the volume of the diluted solution V2. Rearrange the dilution equation to isolate the unknown property, the concentration of the diluted solution, C2. C1V1 equals C2, V2, C2 equals C1 V1 V2. Since the stock solution is being diluted by more than twofold, volume is increased from 0.85 L to 1.80 L, the diluted solution's concentration is expected to be less than 1/2 M. This ballpark estimate will be compared to the calculated result to check for any gross errors in computation, for example, such as an improper substitution of the given quantities. Substituting the given values for the terms on the right side of this equation yields C2 equals 0.850 L times 5.00 mol 1.80 L equals 2.36 M. This result compares well to our ballpark estimate. It's a bit less than 1/2 the stock concentration, 5 M. Check your learning. What is the concentration of the solution that results from diluting 25.0 milliliters of a 2.04 M solution of CH3OH to 500.0 milliliters? Answer: 0.102 mCH3OH. Example 3.20. Volume of a diluted solution. What volume of 0.12 mHbr can be prepared from 11 milliliters, 0.011 L of 0.45 mHbr? Solution. Provided are the volume and concentration of a stock solution V1 and C1 and the concentration of the resultant diluted solution C2. Find the volume of the diluted solution V2 by rearranging the dilution equation to isolate V2. C1 V1 equals C2 V2 equals C1 V1 C2. Since the diluted concentration, 0.12 M, is slightly more than 1/4 the original concentration, 0.45 M, the volume of the diluted solution is expected to be roughly 4 times the original volume, or around 44 milliliters. Substituting the given values and solving for the unknown volume yields V2 equals 0.45 M, 0.011 L, 0.12 M, V2 equals 0.041 L. The volume of the 0.12 M solution is 0.041 L, 41 milliliters. The result is reasonable and compares well with the rough estimate. Check your learning. A laboratory experiment calls for 0.125 MHNO3. What volume of 0.125 MHNO3 can be prepared from 0.250 L of 1.88 MHNO3? Answer: 3.76 L. Example 3.21. Volume of a concentrated solution needed for dilution. What volume of 1.59 mKOH is required to prepare 5.00 L of 0.100 mKOH? Solution. Given are the concentration of a stock solution, C1, and the volume and concentration of the resultant diluted solution, V2 and C2. Find the volume of the stock solution, V1, by rearranging the dilution equation to isolate V1. C1 V1 equals C2 V2 V1 equals C2 V2 C1. Since the concentration of the diluted solution, 0.100 m, is roughly 1/16 that of the stock solution, 1.59 m, the volume of the stock solution is expected to be about 1/16 that of the diluted solution, or around 0.3 liters. Substituting the given values and solving for the unknown volume yields. V1 equals 0.100 m, 5.00 L, 1.59 m, V1 equals 0.314 L. Thus, 0.314 L of the 1.59 m solution is needed to prepare the desired solution. This result is consistent with the rough estimate. Check your learning. What volume of a 0.575 m solution of glucose, C6 hydrogen oxide, can be prepared from 50.00 milliliters of a 3.00 m glucose solution? Answer: 0.261 L. Learning objectives. By the end of this section, you will be able to define the concentration units of mass percentage, mass volume percentage, parts per million, ppm, and parts per billion, ppb. Perform computations relating a solution's concentration and its components, volumes, and/or masses using these units. The previous section introduced molarity, a very useful measurement unit for evaluating the concentration. However, molarity is only one measure of concentration. This section will describe some other units of concentration that are commonly used in various applications, either for convenience or by convention. Mass percentage. Earlier in this chapter, percent composition was introduced as a measure of the relative amount of a given element in a compound. Percentages are also commonly used to express the composition of mixtures, including solutions. The mass percentage of a solution component is defined as the ratio of the component's mass to the solution's mass, expressed as a percentage. Mass percentage equals mass of component mass of solution times 100%. Mass percentage is also referred to by similar names such as percent mass, percent weight, weight/weight percent, and other variations on this theme. The most common symbol for mass percentage is simply the percent sign, percent, although more detailed symbols are often used, including percent mass, percent weight, and with W%. Use of these more detailed symbols can prevent confusion of mass percentages with other types of percentages, such as volume percentages, to be discussed later in this section. Mass percentages are popular concentration units for consumer products. The label of a typical liquid bleach bottle, figure 3.17, cites the concentration of its active ingredient, sodium hypochlorite, NaOCl, as being 7.4%. A 100.0 gram sample of bleach would therefore contain 7.4 grams of NaOCl. The sides of two cylindrical containers are shown. Each container's label is partially visible. The left container's label reads bleach. The right label contains more information about the product, including the phrase contains sodium hypochlorite 7.4%. Figure 3.17. Liquid bleach is an aqueous solution of sodium hypochlorite, NaOCl. This brand has a concentration of 7.4% NaOCl by mass. Example 3.22. Calculation of percent by mass. A 5.0 gram sample of spinal fluid contains 3.75 milligrams, 0.00375 grams of glucose. What is the percent by mass of glucose in spinal fluid? Solution. The spinal fluid sample contains roughly 4 milligrams of glucose in 5,000 milligrams of fluid, so the mass fraction of glucose should be a bit less than 1 part in 1,000, or about 0.1%. Substituting the given masses into the equation, defining mass percentage yields. Percent glucose equals 3.75 milligrams glucose times 1 gram 1000 mg, 5.0 grams spinal fluid equals 0.075%. The computed mass percentage agrees with our rough estimate. It's a bit less than 0.1%. Note that while any mass unit may be used to compute a mass percentage mg, g, kilogram, ounce, and so on, the same unit must be used for both the solute and the solution so that the mass units cancel, yielding a dimensionless ratio. In this case, the solute mass unit in the numerator was converted from mg to g to match the units in the denominator. Alternatively, the spinal fluid mass unit in the denominator could have been converted from g to mg instead. As long as identical mass units are used for both solute and solution, the computed mass percentage will be correct. Check your learning. A bottle of a tile cleanser contains 135 grams of HCl and 775 grams of water. What is the percent by mass of HCl in this cleanser? Answer: 14.8%. Example 3.23. Calculations using mass percentage. Concentrated hydrochloric acid is an aqueous solution of 37.2% HCl that is commonly used as a laboratory reagent. The density of this solution is 1.19 grams per milliliter. What mass of HCl is contained in 0.500 L of this solution? Solution: the HCl concentration is near 40%, so a 100-gram portion of this solution would contain about 40 grams of HCl. Since the solution density isn't greatly different from that of water, 1 gram per milliliter, a reasonable estimate of the HCl mass in 500 grams, 0.5 L of the solution is about 5 times greater than that in a 100 grams portion, or 5 times. 40 equals 200 grams. In order to derive the mass of solute in a solution from its mass percentage, the mass of the solution must be known. Using the solution density given, convert the solution's volume to mass, and then use the given mass percentage to calculate the solute mass. This mathematical approach is outlined in this flowchart. A diagram of 3 boxes connected by a right-facing arrow in between each is shown. The box on the left contains the phrase volume of solution, ml. The middle box reads mass of solution, g, while the one on the right contains the phrase mass of HCl, g. There is a phrase under the left arrow that says multiply by density, gram per meter L, and under the right arrow it states multiply by mass percent as ratio, GHCl per gram solution. For proper unit cancellation, the 0.500 L volume is converted into 500 milliliters and the mass percentage is expressed as a ratio, 37.2 grams HCl per gram solution. 37.2 grams HCl. Answer: 282 milliliters. Volume percentage. Liquid volumes over a wide range of magnitudes are conveniently measured using common and relatively inexpensive laboratory equipment. The concentration of a solution formed by dissolving a liquid solute in a liquid solvent is therefore often expressed as a volume percentage, percent volume, or V/V percent. Volume percentage equals volume solution times 100%. Example 3.24. Calculations using volume percentage. Rubbing alcohol isopropanol is usually sold as a 70% volume aqueous solution. If the density of isopropyl alcohol is 0.785 grams per milliliter, how many grams of isopropyl alcohol are present in a 355 milliliters bottle of rubbing alcohol? Solution. Per the definition of volume percentage, the isopropanol volume is 70% of the total solution volume. Multiplying the isopropanol volume by its density yields the requested mass. 355 milliliters solution. 70 milliliters isopropyl alcohol, 100 milliliters solution. 0.785 grams isopropyl alcohol, 1 milliliter isopropyl alcohol equals 195 grams isopropyl alcohol. Check your learning. Wine is approximately 12% ethanol, CH3CH2OH by volume. Ethanol has a molar mass of 46.06 grams per mole, and a density 0.789 grams per milliliter. How many moles of ethanol are present in a 750 milliliter bottle of wine? Answer: 1.5 moles ethanol. Mass volume percentage. Mixed percentage units, derived from the mass of solute and the volume of solution, are popular for certain biochemical and medical applications. A mass volume percent is a ratio of a solute's mass to the solution's volume expressed as a percentage. The specific units used for solute mass and solution volume may vary, depending on the solution. For example, physiological saline solution used to prepare intravenous fluids has a concentration of 0.9% mass/volume m/v, indicating that the composition is 0.9 grams of solute per 100 milliliters of solution. The concentration of glucose in blood, commonly referred to as blood sugar, is also typically expressed in terms of a mass-volume ratio. Though not expressed explicitly as a percentage, its concentration is usually given in milligrams of glucose per deciliter, 100 milliliters of blood, figure 3.18. Two pictures are shown labeled A and B. Picture A depicts a clear, colorless solution in a plastic bag being held in a person's hand. Picture B shows a person's hand holding a detection meter with a digital readout screen, while another hand holds someone's finger up to the end of the meter. The meter is pressed to the drop of blood that is at the end of the person's finger. Figure 3.18 mixed mass volume units are commonly encountered in medical settings. A. The sodium chloride concentration of physiological saline is 0.9% m/v. B. This device measures glucose levels in a sample of blood. The normal range for glucose concentration in blood, fasting, is around 70 to 100 mg per deciliter. Credit A, modification of work by the National Guard, Flicker. Credit B, modification of work by Biswarup Ganguly. Parts per million and parts per billion. Very low solute concentrations are often expressed using appropriately small units such as parts per million, ppm, or parts per billion, ppb. Like percentage, part per 100 units, ppm and ppb, may be defined in terms of masses, volumes, or mixed mass volume units. There are also ppm and ppb units defined with respect to numbers of atoms and molecules. The mass-based definitions of ppm and ppb are given here. ppm equals mass solute mass solution times 106, ppm ppb equals mass solute mass solution times 109 ppb. Both ppm and ppb are convenient units for reporting the concentrations of pollutants and other trace contaminants in water. Concentrations of these contaminants are typically very low and treated in natural waters, and their levels cannot exceed relatively low concentration thresholds without causing adverse effects on health and wildlife. For example, the EPA has identified the maximum safe level of fluoride ion in tap water to be 4 ppm. Inline water filters are designed to reduce the concentration of fluoride and several other trace-level contaminants in tap water, figure 3.19. Two pictures are shown labeled A and B. Picture A is a close-up shot of water coming out of a faucet. Picture B shows a machine with the words filtered water dispenser. This machine appears to be inside a refrigerator. Figure 3.19a. In some areas, trace-level concentrations of contaminants can render unfiltered tap water unsafe for drinking and cooking. B. Inline water filters reduce the concentration of solutes in tap water. Credit A, modification of work by Jen Durfee. Credit B, modification of work by VA State Park staff, Wikimedia Commons. Example 3.25. Calculation of parts per million and parts per billion concentrations. According to the EPA, when the concentration of lead in tap water reaches 15 ppb, certain remedial actions must be taken. What is this concentration in ppm? At this concentration, what mass of lead, μg, would be contained in a typical glass of water, 300 milliliters? Solution. The definitions of the ppm and ppb units may be used to convert the given concentration from ppb to ppm. Comparing these two unit definitions shows that ppm is 1,000 times greater than ppb. 1 ppm equals 103 ppb. Thus, 15 ppb times 1 ppm, 103 ppb, equals 0.015 ppm. The definition of the ppb unit may be used to calculate the requested mass if the mass of the solution is provided. Since the volume of solution 300 milliliters is given, its density must be used to derive the corresponding mass. Assume the density of tap water to be roughly the same as that of pure water, approximately 1.00 grams per milliliter, since the concentrations of any dissolved substances should not be very large. Rearranging the equation defining the ppb unit and substituting the given quantities yields ppb equals mass solution times 109 ppb mass solute equals ppb times mass solution 109 ppb mass solute equals 15 ppb times 300 milliliters times 1.00 gml 109 ppb equals 4.5 times 10⁻⁶ grams. Finally, convert this mass to the requested unit. Express the mercury concentration of the wastewater in ppm and ppb units. Answer: 9.6 ppm, 9,600 ppb.